Our speaker for today is Professor Stephen Cole, who is a professor of epidemiology at UNC Gillings School of Global Public Health. He works at the interface of epidemiology, statistics, and causal inference. He's interested in study designs and analysis that can accurately estimate parameters of central interest to population health scientists, such as risks, and has been at the forefront of causal inference methods and their applications. Today he's going to talk about how do we ask better questions and get better answers. As researchers, we all have one moment to ask ourselves, what is a good research question, and how can we answer the questions that we are interested in? Today, Professor Cole will go through these two fundamental questions in research in the context of epidemiology research. He will present results from a simulation experiment, which illustrates some features of good answers during nonparametric, parametric, and semi-parametric estimators. He will also discuss what is a well-defined question. And one last note, this meeting is a live event, which means that you can't unmute yourself and ask questions directly, but we have a Q&A button where we encourage everyone to drop your questions during and after the meeting. We'll monitor the Q&A and ask all your questions to Steve as soon as we see your questions. And I think that's it for me. And so Steve, take it away.
Let's see if I can, okay. So some acknowledgements and conflicts. I assume that you guys have a copy of the slides, so I'm going to just skip over some of them and just move into the material. So to start with, if we look at this slide, on the x-axis, we have 13 different estimators. Estimators are just recipes or algorithms to get the answer that we want to get. And on the y-axis, we have the amount of error in each try of the estimator, and there's about 5,000 tries here, the little blue bubbles. So when you're looking at this kind of slide, you might ask yourself, well, which one of these 13 estimators or recipes would I like to use? And I suspect that we want to be as error-free as we can. And that might lead you to estimator 8, which seems to be spot on. 0 error on average, and these are box plots that are over, and it's the tightest grouping of estimates. But what we're going to do is we're going to unpack these 13 estimators and talk about properties of estimators or answers that we would like to have in the machines that we use to analyze our data that we see from the world. We're going to talk about answers first and then questions. We'll probably run out of time and not be able to talk about questions. And it seems like it's backwards. So we should first talk about questions and then talk about answers. But interestingly, the way we work is often backwards. We teach children arithmetic way before we teach them probability, and before we teach them logic. But we know that arithmetic depends on logic. In a sense. So sometimes we actually want to practice. We'll do that here. So what is a good answer? Good answers are robust. And by robust, I mean an algorithm that's not right. It's reasonable answers. It's a broad spectrum of answers. Robust is a term that's used a lot. And I haven't fully explained what it means to me here, but it's the first position, which might seem strange. Most people might answer this good answer with the second one. Good answers are accurate, and I grant that that's true. We want accurate answers, but not at the cost of robustness. I think this is something that we're coming to see. This plays out when we see packages that we share with each other to analyze studies that fail. These are packages that are shared, used, and proffered as good approaches to analyze data, and then we take them and try them in our setting, and they fail. So robustness is coming to mind, I think, as an important aspect of our research. accuracy has always been with us. So where I define accuracy as a combination of low bias and high precision. And we often measure that just so minimizing means for error. Cool. And then finally, good answer for simple, where simple means fast. And that's a third. I'm going to mostly ignore these footnotes, but they're fair game if we get some Q&A. And I'll go ahead and try to stop early so we can have some Q&A. I'll be able to hear. Okay, so we this picture is not quite as good as the mesh, which would better convey the situation, but we're going to dive deeper. I'm going to go a little deeper. This is the here is to picture it to indicate that. So what is this paper from 1994? This is a seminal paper in the statistics literature by James Robbins, Andrea Rotnitsky, and Liu Ping Zhao. It was in the Journal of the American Statistical Association and has sort of helped move statistics from the position of parametric finite dimension models as the standard operating procedure further along the pathway to thinking about semi-parametrics as being the framework used for analysis. And semi-parametrics are a middle ground between the finite dimension parametric models that we may have learned above. Typically, that's maximum likelihood is taught, and semi-parametrics are a compromise between that approach and non-parametric approaches, which make less restrictions on space we're studying. So this is a motivation. You can look at a little example. We're going to take a string of 100 positive numbers, and we're asked to summarize these. This is the kind of thing we need to do in our research. Idealized, simple. So a simple picture that shows all the information contained in the data of these 100 positive numbers would be a cumulative distribution, or a cumulative histogram. Think it's a cumulative histogram. But this outcome y. And that can be defined here as the probability that the variable y is less than some value, little y. We're going to assume throughout our sample units are independently and randomly drawn population without replacement. And so we can ignore issues of generalizability, although generally we shouldn't ignore generalizability. So here's a crucial complication. In these 100 numbers, we're going to have missing data. And to highlight the differences between these estimators that we saw, we got a peek at these 13 estimators earlier. We're going to have missed data on the outcome of interest. So some of the y values will be missing. And be in cases where there either is or is not one auxiliary variable, we're going to call W, is a variable that can help to more accurately estimate the interest parameter. Our interest parameter, or our target, is going to be this cumulative distribution function for y, histogram of y. In scenarios with an auxiliary variable, we still keep our parameter of interest the same. It's now rewritten down at the bottom of this line here. I wonder, can you see my mouse if I use my mouse? Yes, okay. So this is just a re-expression of this cumulative distribution function of y that includes W. So this is where W is coming. Right. So we're going to generate 5,000 samples, 100 units each. We're going to have a covariate that's normal, and it's going to be normal zero delta. And just to reach forward a step, delta is either going to be 0. When delta is 1, W is a standard variable. So good old Gaussian. Delta is 0. Then W is just a unit mass. It's just 0 for freedom. Everybody has 0 variable W. And so essentially W drops out. So we're going to have to study both of those cases. Then the sometime missing outcome y is going to be distributed as shown there, which is a Weibull distribution. And lambda is Weibull shape number, and alpha here is going to be the thing that we're going to talk about. And we'll see about that in a second. So this just sort of walks through the generation of the data. And here we're going to focus not on the picture of y, just the probability that y is less than 1. So we are often going to have missing data. So what I was showing on that one slide was just a FISA court order from the US, which is one of our secret courts, which redacts most of the information that comes out of its notes. And so hopefully we are not being, the redaction is not missing it, not at random. So it's not redaction in the sense to try to help. Our missing data that we get in our studies of the world is not nefarious. That we have missing data because of reasons that we can address via the information that we gather. So what that means is essentially our missing data is missing at random, given measured variables. So when we are in the situation where we're trying to estimate the histogram for y, and we're subject to some missing data, which is this very simple setting, which underlies a lot of what we do, there are different approaches we can take to estimating that histogram. We can take fully parametric approaches, which constrain the model to be one of a family of shapes. Like we can say that this histogram is going to be a normal histogram, or it's going to be a gamma density, or it's going to be a Weibull density, or it's going to be an exponential distribution. And there are a number of shapes to choose from, and any family of shapes has a variety of members in the family. There are a variety of normal distributions with different locations and different fatnesses, essentially, to the distribution, how wide the distribution is. But it can only, a normal distribution can only take one of those possible shapes on. So a nonparametric distribution would be one that can take basically any shape on. So it's flexible. A kernel smoother is a nonparametric approach. The Kaplan-Meier estimator of the survival function is a nonparametric approach. The Kaplan-Meier estimator can look like anything as long as it's a increasing function, decreasing if it's survival, increasing if it's risk over time. Semi-parametric approaches, and the details are sort of on this slide, are a mixture. So some of the aspects of the system that you're studying are locked down to be members of particular families. But some aspects of the system you're studying are left arbitrary, left to be fully flexible. And when we can use such an approach, then we are still able to learn perhaps about the parameter, like the risk of y here that we're interested in, but we don't have to constrain ourselves on the full system so that we won't get part of the system wrong. So the piece of the system that's being left arbitrary, the most common thing you may have come in contact with as an example of this to sort of concretize what I'm saying is a Cox model. So if you've ever fit or worked with a Cox proportional hazards model, you get estimates of the hazard ratio from the model, and that might be your target parameter of interest, but the baseline hazard function is left arbitrary. And that piece of the distribution, you can't misspecify because it's left arbitrary, so you don't have to get it right. So that's the benefit of these semi-parametric approaches, is you don't have to get the whole system right. You only have to get the piece of the system right that you need in order to get your parameter. Maybe we can go to the next slide. So that was that flexibility and therefore the robustness that comes with it makes the semi-parametric estimators interesting. Okay, so over the next 3 slides, I explain the pair of non-parametric estimators that I'm going to use, which are just one, it's just calculating the empirical distribution function at y equals 1. And it's just the average at y equals 1.
And there's two of them. There's one that uses the full data, like as if we didn't have any missing data, which we wish we were in that situation, but we rarely are. And then one where it uses the complete data, where the value, where R equals 1, and R is an indicator of whether you were observed or not. So if we go to the next slide, we'll see the explanation for the, I think, the semi-parametric estimators next. And I again do one with the full data, and then I do 4 of them with just the observed data. So the full data estimators, the estimators that end with an F on their little acronym, are cheating in the sense that they don't have any missing data. So they should work better than the rest. So the 4 semi-parametric estimators here are the first one, the 4 other ones, let's say 4 remaining. Of those, we're going to do a complete case estimator. So it's just, again, using the data where R equals 1, while the SPF is using all the data. And then but it doesn't, that one that uses the complete data, just like the non-parametric one, doesn't try to fix up. It just blindly uses the observed data. Then the 3 next ones say, I got this covariate W. Let me use that covariate to fix up my estimation of Y. And we do that in 3 ways. We first do it using inverse probability weights. We then do it using what's known as the G formula and G computation. And then in the third one, last one here, we use what is known as augmented inverse probability weights, which combines inverse probability weights and G computation. And those estimators are what's known as double robust estimators. So if we get either the inverse probability weights or the G computation formula right, then we get the right answer. We don't need to get both right. Okay, that's the semi-parametric picture. And then there are 2 slides that talk about the set of parametric. There's some more details there on the semi-parametric estimator, which we can just skip over, but I'm happy to take emails if there are questions about this. Then there are 2 slides that talk about the parametric estimators. The Weibull distribution is a common distribution used in survival analysis, and it's described there. And I fit here 3 estimators, one using, again, the full data, which is a little bit of a cheat, one using just the complete data and not trying to fix up the estimator using W, and then the last one, which uses W to try to fix up the estimator. And that last one is actually a parametric version of G computation. It's a G computation estimator or imputation estimator that assumes that the underlying distribution of Y is Weibull. And then we do the same thing with another set of parametric estimators that are exponential, even more restrictive than the Weibull, and that's the next slide. And then we can jump ahead of that. And let's, so another slide forward. Okay, this is just bookkeeping. There was all the actual estimating functions in case you wanted to code this up for yourself. If we go up a little, yeah, so these technical things. We could skip the technical things. So we have 4 figures now. So this first figure is scenario A. And that, if I could see the title, that's where we're under an exponential distribution. When we generate the data, it's under an exponential distribution. I'm sorry, not when we generate the data. When we analyze the data, we're constraining it to be an exponential check that. I was right the first time. When we generate the data, we generate it under an exponential distribution. And we're MCAR. There's no extra leverage in W. The data is missing completely at random. W tells us nothing extra. It's just garbage. That's kind of rude to W. But so here we see that all these estimators work, whether we're non-parametric, which is the first 2 to the left, or semi-parametric, which is this chunk of 5 in the middle, or we're parametric, which is the 6 to the right. Regardless of which way we go, we get the right answer on average. And if you notice here, the best estimator, the one that's most tightly concentrated around a no error, is the full data exponential, which makes sense. There's no missing data, and it's the correct maximum likelihood estimator for that data. We generated with an exponential, we analyzed with an exponential, beautiful. You can't beat number 11 here. You'll see that number, what is this, 10, 9, 8? Number 8 is pretty good. And that's the fitting the Weibull when you generate the exponential. So and the reason that that's pretty good is that the Weibull contains the exponential as a special case. So the Weibull is a little bit less efficient, so you can't really notice it here, but it's a little bit more spread. 8 is a little bit more spread than 11. And if you stare at these histograms and look at the table and think about the 4 cases that we're studying, a lot of the assertions from semi-parametric theory and parametric and non-parametric theory are illustrated in this set of examples. And if this intrigues you a little bit and you wanted to learn more, there'll be a paper that's in press in the American Journal of Epidemiology that will explain these estimators and detail these and some more cases that are not in these set of slides as well. That should be coming out next year. Okay, so this is a nice case. Let's go to the second case. So our second case, the next slide, was figure B. This is now y is still exponential, but now W matters. We're missing at random. Our data is not missing completely at random. It depends on W. And if you ignore W, so any of the estimators here on the x-axis that end with C, remember the ones that end with F that are full data are kind of cheating because they're not having any missing data. So they, as you see, are always going to sit here on the red line. But the ones that end with C are just using the data we see and doing complete case analysis, whether it be non-parametric, semi-parametric, or one of these 2 parametric ones. It's going to be a problem. And that's these 4 box plots that sit below the line. Because we have bias, we have a missing data bias due to W. And the way we handle that is we use imputations or we use inverse probability weights, and that's what you see. So if you look at estimator, let's tell the story going through the estimators 3 through 7. So estimator 3 is the full data estimator, semi-parametric. It works because there's no missing data. Estimator 4, now we're just analyzing the observed data, and it's important. It's a select subset, the observed data, so we get a bias, and we go way off. Now we can account for W in our analysis by using inverse probability weights. That's estimator 5, or G computation, estimator 6, or augmented inverse probability weighting, which is a combination of 5 and 6, and that's estimator 7. You'll note that the IPW is variable, and you may have heard somewhere that using inverse probability weights doesn't have a very tight variance, and that's demonstrated there. And that G computation does better, as you can see, and AIPW will do as good as those or better in a lot of cases. So let's go jump forward maybe 2 slides. I want to wrap up so we can have some Q&A. To figure D, and this is the one, figure D, up 1 slide maybe. Figure D is where we started, and this is the case where we generate from a Weibull, and then and the covariate that we have measured on everybody is important, and half of our Y are missing, and what happens? Well, we see here that the non-parametric estimator only works when we use the full data. The semi-parametric estimator works when we have the complete data as long as we account for it, right, in 5, 6, and 7. And the parametric estimator works if we use the complete data and we correct for it. That's estimator, what's that, 13, 11, that's 10. But the exponential estimators, all 3 of those parametric estimators are wrong because this is Weibull data and you can't map to it. What we get with the exponential is the least false parameter. The exponential finds the place that's closest it can get to the Weibull, but it can't get there. And so that's this bias that we see here on the far right-hand side. Okay, so let's skip down. There's a table that you can look at. Sometimes people like to look at the numbers rather than the pictures, and this would help you. The gold there is the the fact that the full data Weibull can't be beat. That's the parent. That's the oracle. That's the parent. That's what we generated from. So no machine that is not super efficient or using extra information outside of the data could beat that gold standard. And so let's go down maybe to some conclusions. Next slide. So maybe the limitations, let's do those. Limitations are better than conclusions. You can read the conclusions, but let's talk about the limitations for a minute. Go up, yeah, there. So this was experimental work. Experimental work is fantastic in that it, when done right, I mean, it's done by humans, so it's fallible. But when done correctly, experimental work tells us answers that are reproducible and that cohere with the world, but they only tell us the answers in the spaces that you study. So that's the major Achilles heel to experimental work, is it gives you truths, but it only gives you local truths. And it's hard in biomedical research to get global truths. This isn't math, and so we can only tend to be able to learn local truths. Here, that we assume no measurement error and that the data are independent, we could address those issues using the approaches that we're talking about here. And here, we didn't study targeted minimal loss estimators. Those are basically refinement on the AIPW estimator that we studied here that give it somewhat better small sample properties. So the TMLE works a little better in finite samples and small samples than AIPW, but they work the same in large sample theory. So they're in the large samples, they operate similarly. And then we didn't explore here the use of data adaptive nonparametric methods. I like to think about nonparametric methods as type 1 and type 2. Type 1 nonparametric methods are the methods that I learned when I went to school. Things like the Wilcoxon test and the empirical distribution function and the Kaplan-Meier estimator. Type 2 nonparametric estimators are data adaptive, superlearner, other machine learner stacked ensembles. And here we haven't addressed that stuff. And then there might be unrecognized limitations. Of course, there must. I have blind spots, and so there are things that I'm not seeing. And so those things, I'm particularly interested in hearing from others, things that they think I haven't thought of. So those are limitations. And maybe we can stop there and open it up for some conversation.
Yes, that's perfect. Thank you, Stephen Cole, for being a bit flexible here. Well, a first question that I got for myself, but maybe it's because I misunderstood something. But so these things that you showed were all based on simulation data, right?
Yes.
And of course, in simulation data sets, you know exactly what the effects are that you put into the data, but in real data, often you don't. So we saw in one of your examples that when you have missing data, that can impact which estimator works best quite tremendously, actually. But to what extent do imputations or inverse probability weighting fix this problem? Either in simulated or in real data.
Yes. So that's a good question. I would go even a step further than you, and you said that often in real-world data that we don't know the mechanism. I'd say always in real data we have no idea about the mechanisms. Sometimes, we could come. There's a nuance there we could come back to, but so if you have data that are missing at random. And we could go into defining what we mean by missing at random in more detail would be good. But if the data fit the idea of missing at random, then you can recover the data generating mechanism, whether you're generating it or the world is generating it. If the data are missing not at random, then there will be some special cases where you could recover the true data generating mechanism, but often you cannot. Now, in a simulation, we can know whether we're missing at random or missing not at random, but in the real world, we don't know which is going on. And this is the reason that I put robustness at the top of my list, because it's all good and well to be accurate, but we can only test whether an estimator is accurate in given situations. We don't know which of those situations we're in the real world. And so we want an approach to getting an answer that is going to give us a reasonable result across the broadest set of possible settings. And so what do? We make the variable W, which is here just a single variable, we make it a rich set of variables, so that we make the missing at random assumption as broad as possible. And we weaken that assumption so that we're more likely to be missing at random, given 23 variables that the scientists in the subject area feel are very important predictors of Y and predictors of missingness. Then we're much more comfortable about making that assumption. But the logical positivists failed. There is no assumption-free approach to science. Science is a human endeavor. And what we will be best to do is to be open and explicit about those assumptions we're making and the impact they have. And that's a way to move forward faster rather than hiding the assumptions. But I don't want to go on any further. Maybe some more questions.
Yes, thank you. So a practical implication of that would be if you use imputation, include as many potential predictors of that missing data as you can.
Right, and so that brings up the question, and Andrea Rudnitsky, who we mentioned on that paper back from '94, has some really brand new and interesting results on, so what set W should I consider? Is it the predictors of the missing data? Is it the predictors of the outcome Y? Is it just their common causes? In epidemiology, we would sometimes call those common causes confounders. Is it some other set? And it turns out that in very general settings, what you want to, the set W that you want to account for in your analysis are the set of variables that are common predictors of missingness and the outcome, or predictors of the outcome. You do not want to account for variables that are predictors of missingness alone. We might think of those as instrumental variables for missingness. And accounting for those could end up costing you in terms of precision. And in the case where there's unmeasured confounding, it can do something that we call amplification bias. Accounting for those kind of variables, instruments for the missingness, can increase the bias in your estimator as well as decrease precision. So doubly bad. And if people have other questions, feel free to send me an email. My email, I think, is on the slides.
Perfect. Thank you.
And I now see a question from one of the attendees. So is it better to assess which data is missing or try to compensate for the missing data points?
Well, I mean, we often, in the process of trying to compensate for the missing data, we have to understand the missing data mechanism a little bit. And the inverse probability weighted approaches to missing data study that missing data mechanism. And so I think you accomplish one of those tasks on the route to the other one. But ultimately, you have to think about what is your target of inference. What are you trying to learn? What is your question? And that needs to really drive everything else. The question is key. Until you nail down the question, getting answers won't be worthwhile.
Thank you. I see now the time is up for the talk. Thank you very much for the talk, and we apologize again for the technical problems. I leave the final words to my colleague Bing.
Thank you so much for being here with us today, and we apologize again for this inconvenience because of the technical issues, and thank you so much for your patience and support for us. But I think that we have already learned a lot about, from Professor Cole's talk. We know how to use simulation experiment to look for good answers. I think that's a very good gain for us today. And at last, we would like to listen to your advice and feedback for us. So we would be very thankful if you can fill a feedback form for us. And we'll post the link to the form in the Q&A box. And thank you very much again. And see you next time.